All right, I guess that's where we'll get started now. So it's my pleasure to introduce today's CRB seminar speaker, Professor Justin Yim. Justin is assistant professor at UC in Mechanical Science and Engineering Department, where he looks at design and control of legged robots to improve performance and look at locomotion principles. Before joining UIUC, Justin received his BSMS degree from UPenn, a PhD from Berkeley working with Ron Gearing, and then a postdoc at CMU working with Aaron Johnson. You guys can sit on the counter over here if you want. So Justin's work has received the ICRA 2019 Best Student Paper Award and the IROS 2017 Best Paper Award, both looking surprisingly at the same robot, Salto, a really cool one-legged robot. I look forward to possibly hearing more about Salto as well as your more recent work. Everyone, please join me in welcoming Professor Justin.
Thanks, everyone. It's a real pleasure to be here. Really enjoyed getting to chat with people and have lunch with folks. And today, the title of my talk is Small Robots Traversing the World at Large. And I've organized this an increasing number of legs from 1 to 2 to 4. Sorry about the videos not playing, but I think one major theme in the work that I do is looking at how we can get legged robots to be better at getting around in places, looking both at the control and at the mechanical design. There are a lot of places where we'd like robots to go that they're not very good at right now. Natural environments like trees or cliffs or intertidal zones, and built environments like construction sites or really crowded interior living spaces, all would be really tough for robots to get around in. And in each of these spaces, I think that it can be quite beneficial, not only to be a more effective locomotor, but specifically a small one can be really nice too. The smaller a robot is, the less intrusive it can be, the better it can fit into little spaces where bigger ones can't reach, and the more robust it's going to be. If you drop a small robot, oh, not a big deal. If I drop a big robot, that's a lot of bucks. So it's really nice being a small robot, but the challenge becomes maybe even a little bit more challenging when you're smaller, because a little robot has to move around in the same world that a big robot does, and the smaller you are, the bigger everything else looks. So with that motivation, one of the first robots that I worked on as a PhD student, Salto 1P, is this one-legged robot that I brought with me because it's so small. Extra benefit to small robots I can pack in my backpack to bring with me to talks. So hence the title of my talk. Anyway, Salto 1P is a one-legged hopping robot that is designed around this really powerful jumping leg. And the objective we had with building this robot was making a really small package that can still get over large spaces, areas and obstacles that are larger than its own body length. And we did that using a particular mechanical design paradigm, which we called series elastic power modulation. This was a work that my friend Duncan Haldane first started at Berkeley, and really involves 3 main components to this robot. Of course, we start with a really powerful actuator, but that's also coupled in series to an elastic element to make a series elastic actuator, and then finally to a variable mechanical advantage transmission between the actuator and the ground. And together, what this allows us to do is to couple this really powerful actuator with this spring to get a lot of elastic energy stored up in a period before we jump, and then release that quickly and powerfully to launch us into the air. So Salto is about 30 centimeters tall when fully extended, but its maximum jump height is 1.25 meters. So it can, in fact, make a much larger motion than its own size, while still being very small and robust enough that we can do some exciting motions with it. So the actuation here is really important to get that powerful motion to get up into the air, but that's not the only ingredient we need for locomotion. We also need to direct ourselves and stop from falling over. And so for that, there are a few additional actuators that I want to point out. So I've talked about that leg, which is super fun, but in addition to that, we have 4 more actuators. We've got a inertial tail, we call it, if we're in bioinspiration land, or a reaction wheel when in engineering land, that's on the side of the robot, rotating about the robot's, I guess, positive y-axis is what we call it. And this allows us to pitch the robot forwards and backwards in order to have the robot run. We also, though, need to make sure the robot doesn't fall over sideways. And so for that, we have 2 little propellers up on the top. And these are attached to H-bridges, so we can drive them either forwards or backwards. If they look like they were stolen from a mini quadrotor, that's true. We stole them from a mini quadrotor and mounted them sideways, but we mounted them on an H-bridge, so it's a little bit different from a quadrotor. If we drive them forwards, that gives us a positive roll. If we drive them backwards, that gives us a negative roll torque. And we can also drive them differentially, one forwards, one backwards. And because one is ahead and one is behind, that gives us a yaw torque. So we can change heading as well. Putting this all together, we've got a powerful leg that moves up and down in a straight line and allows this robot to bounce, and actuators that allow us to control the direction of the robot. In the initial mechanical design for this robot, we did a good job of packing lots of the mass up at the top. So the leg at the bottom is very light, as are those thrusters on the end. The leg, in fact, only weighs, I think it's like 11% of the total body mass of the robot. So we look essentially like a big concentrated mass on top of a straight line, light, springy leg, which means that we look essentially like a pogo stick. In bioinspiration and in robot locomotion, we are familiar with this model called the spring-loaded inverted pendulum that essentially describes that type of bouncing pogo stick behavior. And a robot actuation is specifically devoted mostly to that vertical motion. We've got a brushless DC motor that's peak mechanical power output is 15 watts, driving that vertical motion. And we've got much smaller attitude actuators that peak out at something like a watt each mechanical power output that then control our attitude. And this allows us to really focus the mass budget and the energy and so on in our robot, mostly in the direction that's most associated with that big energetic change, that bounce, without devoting too much to that orientation. However, even though that orientation control, those attitude actuators are pretty small, they're still pretty capable of getting our robot to move around with that really powerful actuator. And so we are able to get it to do some exciting tasks. Besides just hopping in place, we can also make it run. And we can make it run pretty fast. So the robot's total jump height is 1.25 meters. And the longest long jump is something about 2.2 meters, or 7 times its body length. And the speed that can run at is 3.5 meters per second. And I can never quite get this conversion right, but that's something like 6 or 7 miles an hour or something like that, which is pretty quick for a little robot that weighs 100 grams and is only 1 foot tall and fully extended. And this was the work that we first won our best paper award for at IROS back in 2017. We've got this really powerful actuation, and if we take a look at some of the quantitative measurements of this, the height versus time, it's also relatively extreme in the amount of time it spends in the air versus how much time it spends on the ground. In fact, the robot only has a stance time when it's contacting the ground of about 100 down to about 70 milliseconds at the very lowest. And over that total time from one jump to the next, that makes it spend 92% of its time in the air and about 8% of the time on the ground, which is really quite low, much, much lower than animals and much lower than most other robots. As a consequence of this really powerful motion, the robot's acceleration is really high. It averages during the stance phase about 13 Gs, 13 times gravity, which is a lot. And it's actually kind of a cool trick. The robot is bouncing so quickly with that 13 G acceleration that it sort of dwarfs the acceleration due to gravity. And as a consequence, if the robot is bouncing off of a vertical surface, or if it's bouncing off of a horizontal surface, the dynamics look very similar. Whether 1 G is pulling down or 1 G is pulling sideways, we've still got that 13 G acceleration coming off the surface, which allowed us to make the first ever robotic wall jump. So for folks who have played video games where you can have a platform king character who can jump off the wall and get higher, that's what we aim to do here. The robot jumps 1 time off the ground, reorients itself back towards the wall using that reaction wheel, and then leaps a 2nd time off of the wall to get even a little bit higher than it could have off of the ground in a single jump. And so now we've got a robot that's got this really powerful actuation that we can control. And we don't just do the same thing better, we can actually do new things that wouldn't have been possible without that really powerful high acceleration actuation. Because we accelerate so fast, we can get off of these surfaces that have a different orientation to gravity. And that also means that where previously this wall might have just been an obstacle, we can now treat it as an opportunity to make new motions and get to spaces that are a little bit higher than we would have otherwise. And following this, the next work we want to do on Salto, I'm going to give a pretty quick run through for Salto so we can talk about some of the other stuff. One of the next things we wanted to look at is, okay, well, it's powerful, but can we really direct it accurately to go where we want? How well can we do that? And we looked back at this spring-loaded inverted pendulum model and did some work on more accurately modeling the robot's behavior, which conveniently was quite easy for us because we put a lot of design work in the beginning to make a robot that was very reliable and repeatable and has a very simple to model behavior with a straight line leg that's kind of springy. So we took the classic paradigm for controlling these hopping robots of choosing the landing leg angle in order to direct its next motion. This is the same strategy that was famously used by Mark Rabert, founder of Boston Dynamics, back in 1984, when Boston Dynamics was just barely a dream in his head, to get hopping robots to jump around. And what we did essentially was do a very good calibration for our robot so that we have a good map between if I know what velocity I'm coming in at, and I know what angle my leg is at, what velocity I'm going to bounce out at. Conveniently here, another thing to note is the surface of the ground angle actually doesn't matter too much in this case, as long as you don't exit the friction cone. As long as the forces of the foot always act through the ground, when the robot's pointy toe touches the ground, that looks like equivalent to being a ball and socket constraint with the ground. And it doesn't really matter what angle the ground surface is at, that's still the same ball and socket joint as long as it doesn't slide. So that makes this problem really quite easy. And we did a pretty good calibration of that in simulation, which was accurate enough that we could get the robot to do motions over large objects without falling off. So here we have a table and desk, a chair and desk. The chair is like 50% taller than the robot. The desk's, I don't know, 2.5 times taller than the robot or something like that. And here we're really now starting to deliver on that initial promise of making a small robot that can get over large obstacles bigger than itself. But in order to do that, we have to be careful about not running into objects prematurely or falling off of them prematurely. But again, with a well-calibrated model, we can do that, and the robot can follow this series of waypoints to jump at each of these points in turn, to get up over these things without running into the edges of tables or chairs, adding energy to get higher, and then subtracting that energy and coming back down off of those objects again. And this, I think, is really the thing that I was hoping to do when we were building up this robot in the beginning. Can get it to do these big motions over real objects, show that you can be small and still get around in the big world. And this is our demonstration of that. So there's more that we can do with this too, though. When we have a good model of how well the robot's orientation controls its velocity, we can also flip that problem around and start worrying about estimation, which is not something I've talked about in this talk yet, because in all of those previous videos, you've seen that the experiments have been running in the same room. And the reason is because this is the motion capture room. That's where all our expensive high-speed infrared cameras are mounted on the ceiling, just out of frame, to measure the robot's position at 100 hertz to better than millimeter accuracy. It's every dynamics control person's dream, right? We have high accurate feedback, and so that's really convenient. But there's no way I'm going to go take a tens of thousands of dollar motion capture system on poles and run it around outside if I want to go and use my robot somewhere. So let's actually solve that estimation problem as well. There are a few things that are going to be important for that. One of them is the velocity of the robot, right? I want to control what speed it's going at so it doesn't run into the wall or go the wrong way. But I also need to know the angle of the robot. Each of these have been measured before. For the velocity, we can get encoders in the leg, tell how fast the leg is moving when it's in contact with the ground. We know the velocity. When in the air, easy, parabolic motion. Once I'm in the air, I'll just project that forwards with parabolic motion and things are good. Attitude seems like it should be easy to solve too. The usual way we'd go about doing that is with an inertial measurement unit, or IMU. And those are generally a combination of rate gyroscopes that measure angular velocity and accelerometers that measure the acceleration due to gravity. The rate gyroscopes give us a great signal, but it's subject to drift because we're integrating a rate. The accelerometers cancel that by measuring the difference from gravity and give us this low rate, though not as accurate feedback signal on the angle. Awesome, seems like it should be pretty good, except there's one challenge, and that is for this bouncing motion that the robot makes, we're always in one of two states. Either we're in free fall or we're bouncing off the ground. When we're in free fall, the accelerometers uniformly read 0, and so they're of no use. But when we're bouncing on the ground, I already mentioned the robot's accelerating at 13 Gs, and it's only spending 70 milliseconds on the ground, while also vibrating and shaking from having just impacted the ground. Meaning we'd be looking for a 1G signal behind a 13G bias with a lot of noise, and we're trying to do that in 70 milliseconds. Seems like a pretty hard estimation task. So we said, let's not worry about the accelerometers. Let's see if there's something else we can do instead. And that was fit using the proprioceptive velocity sense to direct the attitude. And conveniently, we'd already done a lot of that work previously to get the robot to jump accurately. Remember, the first model that we made was mapping the incoming velocities to the outgoing velocities through this parameterization of the leg angle. So if we trust that our controller is very good, essentially what we can say is, if our outgoing velocity is not what we wanted, but our controller really thought that was the right angle, well then maybe the angle is wrong, not because the controller's at fault, but because the estimator's at fault. If the estimator tells you a certain angle and I go to that angle, but the estimator was off by some amount, my velocity will be wrong by some amount scaled by that error. So as I swing the leg forwards and backwards, I have a mapping that tells me how fast I expect the robot should go, and I can apply some really simple feedback. Here I say that my error in my angle is going to be approximately proportional to some gain times my velocity error. So that's sort of working that problem backwards. If my velocity is wrong by this amount, then I guess my error must have been wrong by that amount. And then minus this other term is subtracting out the control error. So if my controller didn't actually converge to the desired end result, and I still have some residual error left, I'll subtract that out because I don't want to count that. I only really care about the estimator component. And we tested that out in experiment. So we tested this out by having the robot autonomously attempt to hop in place. And this is the paper that we got the best student paper for afterwards, because I ran a live demo at the conference. I unfortunately can't bring a live demo today because I didn't bring the controller for my joysticks. But in any case, here we had the robot running autonomously, so no input from anything else externally, except for one little trick. Here we told the robot to hop in place and stay relatively close to this white arrow on the floor, but partway through this motion, we sent a software signal to corrupt its attitude estimate by 5 degrees, and specifically to make the robot think that it's tilting 5 degrees back. This makes it overcorrect by tilting 5 degrees forwards when it lands, and without any correction on the top, the robot just keeps hopping forwards until eventually runs into the wall and falls over. With our corrector, then we can recover our attitude estimate by measuring that error in velocity, comparing that to how fast we thought we should be going. And when we plot the attitude estimate error over time, without any correction, when we get an error, it stays there forever. If we're integrating a rate on the gyroscope, it's never going to disappear. And with our corrector, it converges in less than 10 steps or so, something like that. And we're able even to start recovering back to that initial position we want it to be at. So this is what allows us to get our robot to hop around outdoors under joystick control, which was really a lot of excitement. It was really a lot of fun to puppet the robot around like this. And we got some nice video footage with the video people on campus. So, okay, great. We've got a little robot that's really powerful. It can make these big new motions. It can move over large obstacles. It can do that precisely, and it can estimate where it's going. We can run, we can hop, we can jump off of walls. There is one thing, though, that we can't do and hasn't been shown in this talk, and that's we can't stand still. The robot has never at any point stopped moving once it started moving. And that's because if you're using your leg angle to control when you hop, when you hit the ground, you don't get up again. You don't have another choice of what your leg angle is going to be. So we need a different model for doing that. And specifically, we want to have a different model of how the robot balances on the ground in order to make it stop and actually stand still, like that. And so this is the problem of essentially getting the robot to stick a landing like an Olympic gymnast with feet together, right? A small contact area on the ground, and you don't want to take another step. For a gymnast, if they don't quite make it, they take a step and lose some points. For a robot with only one leg, there's no other feet to take a step with. You're just kind of done. So the robot is not currently capable of getting up, and so it's really done if it falls over. So we need a good high-performance controller to do that type of balance. And here, we specifically focused in the sagittal plane mostly, where we're doing those running and jumping motions. And we worked with Roy Featherstone in Italy, who's a really famous dynamicist, and looked at how to balance a reaction wheel inverted pendulum. This is a model that some of you might have been familiar with from controls classes, and consists of a spinning mass on top of a rod. And conveniently, the dynamics for this can be simplified quite a bit by looking at the angular momentum about the contact point with the ground. If the only forces are gravity and that foot contact at that point, then if you take the momentum about the point of the foot, then all the forces through that don't matter. They don't have any moment arm. And so the only thing that's going to change that angular momentum is the gravity vector shifted away from that foot. So if you integrate the distance of the robot away from the center point times mass times gravity, that is your rate of change of your angular momentum. So that allows you to build this high-performance balancing controller, which he had previously published and which we implemented for Salto. So the next thing we looked at was, this controller is great, it's pretty good, but we know that it's hard to make this landing, because if you pick sort of the wrong angle to land at, you're not going to have enough oomph in your reaction wheel, enough torque, enough control authority to get yourself back up to upright. So we'd like to be able to pick the right angle in order to make that landing. And so we looked at the problem of If you choose a landing in which no control effort is required at all, where you passively swing up to vertical through conservation of angular momentum, that would be a good point to pick, because then you're in the center of your actuation space and you have a lot of flexibility on either side, a lot of margin to recover from errors. So picking this angle, I don't know if I'm going to go through all this math, but we can do some conservation of angular momentum and linearization and come up with an approximate angle, which works pretty well, which we can also then do some manipulation on. Because we have a really nice, simple expression, we can also take the derivative of this expression with respect to different parameters to see how sensitive we are to errors. Essentially, how far over could the robot lean to one side or the other before it's going to be unrecoverable and where the robot won't be able to balance. And we came up with a simple expression for that by doing a little bit of differentiation. And if we plug in numbers for that, falling from a height of 1 meter, which is just a little bit below Salto's maximum jumping height, then we have an error of only about plus or minus 2.3 degrees, which is great at giving us an intuitive feel for why it's so hard for Olympic gymnasts to make that landing after a floor routine. They've got a really small margin to work with. And Salto actually has quite a hefty inertial appendage, this reaction wheel to spin, that acts sort of like a gymnast's torso or maybe arms when they're trying to not fall over. So it's really quite a challenging task when jumping from high, but our attitude to actuation from before is accurate enough that we can do this pretty well across a range of different jump heights and jump angles, forwards and backwards. And we got the robot to succeed in, I think it was 55, 57 out of 60 trials. I should go back and double check the numbers in this, but reliably enough that we could get the robot to stick those landings most of the time. And once we're on the ground, we can actually reuse that balance actuation to get even more precise jumps than we did on the chair and the desk. Here's an overlaid video of 10 different trials of the robot making a launch using that balance control to lean to a desired angle and then jump over a body length. The standard deviation in the X displacement is only 1.6 centimeters, which is so accurate that I've got like a 90+% confidence that if I had the robot jump a full body length to my hand, it could probably do it, which is great. At this point now, we've got a little robot that can also precisely place where it's going to go. So if the terrain is not only larger than its own size, but has features that are smaller than its own size, it can jump to those and land on them. So we demonstrated that here, having the robot jump to 2-inch wide pieces of tape. Here we use the motion capture system just to tell the robot where the tape is, but not to do the onboard control. And then it lands on each of those pieces of tape, sets itself up to balance, and then jumps to the next one in sequence because it's reliable enough to do each of those in turn. And that is essentially the last work that I finished up for my PhD and the story of Salto. So before I move on to the next part, I'm happy to take any questions. I've been going pretty quick, so there haven't been any so far. Before I go into the other ones, does anyone have any questions about Salto? Yes.
Seems like you've sort of like all of the possibilities is very good. But I was wondering, isn't the energy stored within the elastic element of that ever a problem when you come from a large height to a small height?
Yeah, okay, great question. If we want to stop moving, we'd like to remove all the energy from the system. We've got a spring in series, which is going to get wound up when you hit the ground. Indeed, the spring is a challenge when you're trying to land. But because the motor is powerful enough and fast enough, what we do is as the spring gets compressed, we unwind that to take the energy out. And because we've got a series elastic actuator, we can measure the force that's applied to the ground by measuring the deflection of the spring. And we write a force feedback control law that attempts to emulate a damper, which then removes all the energy from the system.
So kind of buckles the actuator.
Yeah, so the spring winds up, the motor unwinds it before the spring snaps back, and then that keeps the energy out of the robot. Yeah, good question. Others about Salto? Yes, go ahead.
Following up on that, do you save that energy that you remove through virtual damping, like through regenerative braking, or just burn it off?
No, right now when we're landing, we just burn that energy. When we're hopping, usually we get to use that energy again, and that's because when the robot hits the ground, the spring's going to compress from that initial negative velocity, and we start the motor at some initial angle. But we just drive the motor forward, so the motor is always doing positive work. And when the robot takes off again and the spring unwinds, we get back both some of that extra energy the motor has pumped in, plus some of the energy that was stored. And our energy return, our essentially coefficient of restitution is about like 60-something%. So we get more than half of the energy back on each hop. But when we have to stop, we need to get rid of that energy and currently we just burn it. All right, great. Yes.
So you are only applying, giving the main motor, the motor that drives the legs, power when you're touching the ground in that 70 milliseconds, or are you always trying to store the energy in some energy storage?
Another good question. So the spring is series elastic. There's nothing on the other end except for the ground when we're in contact with the ground. When the leg is in the air, if I spin the actuator, the leg just changes length, but the spring stays at approximately 0 rest length as the crank angle changes. So we can only really add more energy to the spring when we're in contact during that 70 to 100 milliseconds on the ground, meaning that the motor has to be relatively powerful.
Okay.
Yeah.
That's why you're using like a 30 watt. Or
Yeah, that's right. That's we have a 15 mechanical power output motor. Yeah. Okay, great. So, okay, one last question, then I want to continue.
I'm just curious, what's the operation time of the robot?
Yeah, well, so because we can capture a lot of the energy back while hopping, the robot can hop for, I think about the longest test we've ever done is 12 minutes of continuous hopping, but we still had some additional energy after that. So the total lifetime is maybe a little bit longer than that. I don't know exactly how long.
Okay.
Yeah, and that's with a 220 milliamp hour 4 series LiPo battery. Okay, great. Well, I want to talk about some of these other robots that I've worked on since my PhD. And these are things I did as a postdoc at the Carnegie Mellon Robodynamics lab with Aaron Johnson, who Shane was also a member of while there. And one of these robots was a little biped robot where we were looking at the mechanical design of walking. In particular, we wanted to see, could you build a really tiny walking biped robot? It gets harder to walk at smaller scales, and it gets really hard to build them at smaller scales. But we'd like to build them at those scales so we could sort of investigate what that scaling looks like. Where is walking efficient? Where is rolling more efficient? What does that trade-off look like as the scale changes? A lot of those questions are kind of tough because you'd have to worry about things that change, like electrostatic adhesion or friction or these other terms that are difficult to model with kind of classical rigid body mechanics, and we'd like to investigate experimentally. So we didn't get all the way to that point in this project, but we did focus first on how do we get designs that one could scale up and down to vary the different sizes of a biped walking system and then compare them. So we wanted a system that was going to be really simple to build and also really simple to control. The smaller you get, the faster the time constants are for your system and the faster you have to control things. While at the same time, you have less sort of onboard payload capacity for computation and powerful actuators and so on. So we wanted something that was going to be really, if you had few moving parts and also had, if possible, stable operation. So we were inspired by the passive dynamic walking robots of the past, including this passive dynamic walking toy from more than a century ago that waddles down a hill like a penguin. I think someone already mentioned about the walking robot. So these are little walkers that have 2 feet with rounded ends that will waddle as they descend a slope with no energy input. Of course, we want a robot to actually be able to walk on flat ground, so we need to add actuation, and we did that in 2 ways. We built some robots that are about 6 inches tall just to prove this concept, one of which extends its legs in order to lift up its feet, and the other of which has only 1 motor rather than 2, and swings the angle between its legs to change how it walks. We call these the leg extension walker and the hip actuated walker. On the left, this robot consists of about 5 rigid bodies, feet on the bottom, upper legs, and then a torso with a pin joint between them. So the upper legs are pinned through that torso on the sheared axle. In the hip actuated robot, that one actually only has 2 rigid bodies and 1 motor driving its single pin joint. The way we achieve that is, it's a little bit hard to see in this picture, but maybe I'll skip ahead as I did earlier to this one. The robot on the right is another version of our hip actuated walker. It's got 2 arms and it's got 2 legs, but the right arm is rigidly attached to the left leg and the left arm is rigidly attached to the right leg. So this robot only has 2 rigid bodies, which we think makes it perhaps the simplest walking robot that you could build that's still able to do these motions that I'll demonstrate in just a second. So these robots are quite simple, but we wanted to make sure that they were going to be passively stable when they walked, and also maybe steerable would be a nice feature. So let's look at being passively stable to begin with. These robots also have rounded curved feet, and we made sure to place the center of gravity of these robots below the center of curvature. So this means that, like one of those top tipping toys, if you give it a push, it will naturally passively come back to center. In order to get these robots to walk forwards, though, we had to make some tweaks. On the left, our robot with the extending and retracting legs has actuated leg length, but an unactuated pin joint at the hip. So in order to get the robot to walk forwards, we had the robot sort of lean forwards a bit. The hip pin joint is displaced ahead of that CG center of curvature axis. And that means that because it's ahead, when you pick up one leg, it's naturally going to want to swing forwards because the pin joint is ahead of it. And then that will make it take a step forwards. Conversely, for the hip actuated robot, when we wanted to take a step forwards, initially both feet are on the ground, and I'm just going to rotate the hips without picking the legs up. So I need to slide my feet on the ground. Whichever one goes forwards is the one that's going to be the front leg, and I want to bias the robot to go in one way rather than the other. Turns out if you lean the robot backwards, it's going to pick up its a foot that goes forwards. And the way you can think about this is if the hip joint is displaced backwards, when you try to swing those legs, the one that's moving backwards is going to be pushed down into the ground, and the one that's going to move forward is going to be picked up off of the ground. And so that's the one that's more likely going to break friction and come up. So that's the intuition there. So this allows a robot to be self-starting. It can statically stand on the ground based on the location of the CG. And once you turn the robot on, it walks away. And same thing for the one with the hip actuator. Once you turn it on, there it goes. So there's another parameter that was important is also the frontal plane radius of curvature. So we need that same model of those rounded feet with the center of curvature above the center of gravity for the robot. And we actually investigated different strategies for doing this. We could have one shared sphere from which both feet are cut, and we just cut a wedge out of the middle. We could have that shared sphere and cut it in half and have the two legs touch each other. Or we could take that shared sphere, cut in half, and then separate the legs out sideways. And that's what's drawn here. Each leg has a separate radius of curvature that's displaced left or right. And that makes sure that the feet are tangent on the ground when both of them are flat. And we investigated how each of these changes the effect of the robot's walking and how stable it is. And you'd think, okay, I mean, that's just a centimeter difference in this. It's not going to be a very big difference. But from simulation work that we also very experimentally validated, we saw that there actually was a pretty big difference in what range of actuation parameters you could use in this robot that would work. So these are all data collected for the leg extension walker, which is a little bit easier to work with for this type of experiment, where on the right axis, we're changing the amplitude of how much we extend or retract the legs. And on the vertical axis, we're changing the frequency with which we extend and retract the legs. And we've color-coded this based on whether that combination of parameters produced a steady walking gait in green, an unsteady, wobbling, chaotic gait in red, or a leaning gait in which it was stable, but it was leaning to one side. So first, a chaotic gait looks something like this. The robot kind of totters to one side. It might kind of lean one way, then lean the other, and it's not very predictable, meaning this gait doesn't work very well. In the leaning case, the robot settles into a steady gait, but leaning to one side, it has a tendency to curve one way. And in green, this is what we want. The robot starts up and very quickly settles into this gait where it toddles back and forth in a reliable way. And sort of surprisingly to us, the non-concentric feet with those two separate radiuses of curvature that are tangent to the ground at the same time when they're both down was the best. So that's the one that we chose for these robots. So with that design now for the sagittal plane, that's the front backwards motion robot, and the frontal plane, the left right rolling, we now have a robot that could self-start, that was stable, that could walk really nicely. The next thing was, can we get this to turn? So for the leg extension robot that has the two different feet, this ended up being a pretty easy way to do that. If we start out with the 2 feet exactly out of phase, then we can shift a bunch of different things to make these asymmetric, but one easy one is just to shift the phasing of that. And if we change the phase here, we can get the robot to have different radiuses of curvature, arcing slightly towards the left or towards the right. And another strategy that I won't bother showing here for time is if we also wanted the robot to make a really sharp turn to one side, we could just turn off one actuator and kind of do, this thing, dragging the other foot behind it. And then that got me to do a very slow, very tight turn. But maybe the more interesting question for me was, can we do it with one actuator? Can a single actuator robot not just walk forward in a straight line, but also turn? And the answer there is if we can introduce some type of effective asymmetry to this robot. Our control signal is now just one line because that's the relative angle between the two legs as they swing back and forth. But we still have a way that we can introduce asymmetry here. We just can't keep it a sinusoid. If you make the sinusoid spend more time on one side and less time on the other, or if you make it swing forwards faster and backwards slowly, then that is a way that we can get the robot to bias itself towards one side or the other. And indeed, by doing a different leg swing pattern like this, we can make the robot turn towards the right or turn towards the left And it actually has a tighter radius of curvature than the two-legged robot, the two-motor robot had. So the first robot, the leg extension actuator paper, we published at ICRA 2022, and this second one is actually not published yet. It's coming out at Humanoids this year, I guess it's December. So we're really excited about that, and excited that we could demonstrate these designs of robots that in the future we could scale down to make into little robot designs that we could use to investigate scaling and locomotion at different size scales. All right. Any questions before I finish up in the last 10 minutes? I think I'll be on time with the disentangling project with 4 legs. Yeah.
Can you put on the what heel? It's kind of like demonstrate on the flat.
Yeah, okay. Can the robot walk up a slope? In this case, unlike Salto, this robot is not very good at obstacles that are large in comparison to its body. If you put even like little bumps down on the ground, it starts behaving pretty weird. So the leg extension walker here can walk up mild slopes and can go over small bumps. But I mean, more than a few degrees, and it probably wouldn't work very well. And part of that is also because of the way that the hip is biased forwards. Once the slope of the ground causes the robot to lean backwards too much, it doesn't walk forwards anymore. For the hip actuated walker, it's really in this kind of delicate balance where you only have one motor that's trying to coordinate the swinging of the legs, the rocking forwards and backwards along that foot in the frontal plane, and the rocking side to side. It's got multiple different oscillator motions that are trying to be coupled. If it gets disturbed by a pebble on the ground, it's really doing crazy stuff. So it's not really good at that. But it is very simple, and maybe that's the trade-off that we found in this robot. Very simple, but perhaps we've lost some capability.
Thank you.
Good question. Yes.
Steven technology decided made it important for the center of mass to be below the center of curvature.
Yes.
But if within the tipping range, if the center of mass is within the support polygon, it shouldn't be above this, right? So it's not a necessary condition for it to be like below that point, right?
Yeah, okay. So you were talking about the support polygon here. So actually, it turns out that the support polygon for this robot, while it's in single support phase, is really only 1 point. It's the contact point of the foot with the ground, because the ground is a flat plane and the foot is a sphere. The contact point is only this single point. And so I don't know why it's auto advancing, but the challenge is that if the center of gravity is above that point, when the robot tips, the center of the contact point with the ground moves over by some amount, but the CG moves longer. So it's going to move faster than that point and get away. Other way around, if the CG is below that point, then the point will advance faster than the CG and it will push it back towards center. Yeah. Okay, great. Let me talk a little bit about the last project I did. And this was the main project I worked on during my postdoc, funded by the CI Fellows, CI Computer Innovation Fellows Fellowship. And this was looking at getting robots to be better at walking through plants. So we want robots to be out in the real world. The title of this talk was Small Robots Traversing the World at Large. And there are lots of other types of obstacles that can get in their way. When you're a small robot, obstacles like plants can be an important feature, but they can also be a really great opportunity for small robots to operate. Unlike big tracked vehicles, we don't have to crush all the plants in our path. A legged robot should be able to pick and choose its steps to get through underbrush or vines or whatever, but it's also likely to get caught on these. And in fact, current legged robots at a relatively small scale, like this one here, which is similar in size to the Unitree Go 1 that we've got, I saw in the lab here, gets really stuck with the initial commercial controllers here. Stepping low, stepping high, walking backwards, walking forwards, nothing works. The robot is really quite jammed in the vines here. And we wanted to figure out, this robot feels like it should physically be capable of doing this motion. In fact, it should even be physically capable of sensing the problem here, that it is stuck on vines. But we just don't have the right algorithms to do that. So can we come up with the right strategy to detect and disentangle from these numerous flexible, unavoidable contacts? Here, it doesn't seem like vision sensors and the classic motion planner are going to solve our way out of this. If you see a bed of vines or a bed of grass or something, you have to touch the grass to go through the grass. You're not going to be able to avoid it just because it looks like a solved obstacle. You have to push through it. At the same time, those vines or leaves or grass could be hiding rocks or vines or other things that you'll actually get stuck on. So you need to be able to detect when you're stuck on that and then get out of it. And we tried first to approach this task by doing a few simple things to say, okay, maybe we want to make sure that there's some, really quick, easy solutions that we could use instead. And if these work, we don't have to worry about this problem. Maybe there's a really simple way for us to walk through these vines. Maybe we could make the robot walk backwards. And indeed, if the robot walks backwards and the vines are low enough, they slide underneath the heel. But if they're too high, they can get caught on the knee. And then in this case, this is a pretty extreme example. The robot falls over because the vine unbalanced it enough. Another strategy might be, okay, what if we just step really high? If we step high enough, we should get over everything, right? Well, if you just kind of naively pick your feet up, then that will work sometimes, like here. It gets over the vine the first time, but the second time, because the leg reached the vine at the wrong phase, it caught the vine rather than getting out of it. And so here it would still got stuck again. The last thing we could do is we could think more carefully about how to retract the legs so it doesn't get stuck on stuff. And this was stuff that we actually is an implementation of our later controller, just tested retracting its legs all the time in order not to get stuck. And the gate looks a little bit funky because it's just like, no, booty's on, right? That's the kind of thing that the dogs do when they don't like wearing stuff on their feet, right? So it works fine, but it takes a lot of power, almost double the amount of power the robot normally takes when walking, which is really quite saying something because I'd expect most of my effort should be spent on doing the push-ups on the ground to hold myself up, not swing my legs around, right? So that's not a very efficient gate that we've got going here. So let's try to do something a little bit more intelligent. Let's get ourselves unstuck when we notice we're stuck, but not do it all the time. Let's detect when that happens. So our problem setup was to keep things simple and to do this first approach into getting robots to walk through vines. We've limited our problem to let's do forward motion in the sagittal plane. Let's walk in a straight line. And we're going to consider the obstacles that are in front of us to be something like vines or cords or something like that. And they could have stiffness and damping that we don't know, and some friction, but they're not going to be very massive. So we're not going to have to worry about these crazy oscillations of what's it called, diving boards or something that are running to the robot. Well, we won't include additional state in the environment that way. And so we'll not simulate them as being these sort of spring dampers without mass that also have friction that could get stuck on the legs. That also seemed like an important factor that would get you tangled. And finally, we assume that we've got a relatively well-behaved substrate that's going to be relatively flat and hard and grippy, so we don't have to worry about that too much. So our solution was, let's focus on the swing legs. That is the legs that we're picking up and trying to get forwards. If they get stuck on something, we want to be able to detect that and then get them unstuck. If the robot's foot is on the ground and it's running into obstacles, well, I mean, it's supposed to be running into the ground, so maybe that's not so much of an issue. We're going to be in more trouble if the legs that are supposed to be advancing are not able to, because that's really how you trip on things if you sort of intuitively think about it as a human. So let's get the swing leg to detect those contacts and then pull itself out. And the first thing we set was a momentum-based observer that takes advantage of a particular feature of modern quadrupeds. They're built with very transparent limbs. That means that they don't have a whole lot of mass. And if you push on them, it's easy to detect changes in the motor current and velocity to tell that there's a force being applied to that robot limb. In other words, it's easy to backdrive them. These have highly backdrivable limbs. So with that, we can track an estimate of force on the robot's legs like this. And here in the gray regions, the legs on the ground. In the white regions, it's supposed to be in the air, specifically the front right leg. And we can see while the robot's walking, the force is relatively low on the ground until the foot gets really stuck. We start seeing in that white portion a large negative force that's keeping the foot down and pushing it backwards. So this momentum-based observer is able to detect that relatively quickly. And we made a few additional adjustments to this that were suited specifically to the task of detecting these light obstacles. For one, we only cared about forces that are pushing the leg backwards. If something's pushing us from behind, well, the ground is pushing us sort of from the behind the limb, so that's good. And we also reset the momentum-based observer every time the foot came off the ground. The reason for this is because the momentum-based observer is tracking how much force is applied to the limb, but there is a first-order convergence to the true force. So it's sort of like there's a first-order low-pass filter that's going to be applied to the signal that's coming through your estimate. And if you have your foot on the ground, applying a large force to keep you upright, and then you pull your foot off the ground, it'll look like there's still a large negative force that's pushing the foot upwards. And so we canceled that so we can detect it a little faster. In any case, we're able to detect that relatively effectively. And then we designed a relatively simple retraction strategy that attempts to lift the foot up while applying a light forwards force against whatever obstacles are on the robot's limb. This way, we don't run into cases where the robot tries to pick its foot up, and then the branch gets unstuck, and we think we're unstuck, and we hit it, and we go back and forth and have a kind of crazy behavior. But we only apply this strategy once we detect the robot's limb is stuck on something. So for different stiffnesses of terrain, that reaction triggers at different times. If the ground is very stiff, we immediately retract the leg to get it unstuck from something. And if the ground is very soft, we don't have to really worry about stuff until the force is large enough that it would actually start to impede the robot's progress, and then we can get unstuck. The robot will then track the momentum-based observer to see, am I unstuck from this thing, and keep trying that retraction motion until it's unstuck. And then after that point, it will advance the foot again. So this works pretty well. So some early versions of this we also test in simulation against full inundation from head to toe. And again, this same kind of retraction strategy still works as we sweep this leg through a big field of vines. So we tested this experimentally against a variety of different soft and hard obstacles, a bungee cord on the left. And again, the robot advances until the force is high enough that it gets in the way of the legs, and then it walks through it. And here on the bottom, a very hard aluminum beam, which the robot also disentangles from. So this strategy uses approximately the same amount of energy as the regular walking when it's unobstructed, and a large amount of energy when disentangling, but much less than the always high-stepping, I've got booties on my feet and I don't like it, dog walk. We even tested this against a mix of different stiffnesses all at the same time in the laboratory. Here are some bungees and some stiff ropes, which the robot can get through, even when multiple limbs are stuck. Some of the legs are a little confused and think that they're still stuck on something, but it does eventually make it through that. And finally, we tried this outdoors in that same bed of vines that I guess the gardeners killed over the when we took the first video and the last one. But trust me, it's the same vine bed, it just doesn't look the same. And we compared it against the default controller. Here, our robot was developed mostly using motion capture, so the onboard state estimation wasn't super high performance, but we can still do a comparison of the default controller that got stuck immediately and fell over, and our controller that made it much further before the state estimation got confused and knocked the robot over. So we got some real outdoor experiments, and the robot is able to work. And in the future, we hope to get some better state estimation onto that package. So finally, to wrap up, I'm really interested in both the mechanical design and the control and estimation, here using Salto as that example. And I really like to think about reduced order models of energy and steering for how I design those robots, both on the control and the design side, and then evaluating these in the foundational performance, sort of the speed, the payload, how much my robot can do, as well as how well it works when we're in challenging terrain. And in the future, I'm excited about building more robots that do different types of motion, walking and climbing and running and so on, maybe even slithering and rolling, and working with students on those tasks. So I'm just building up my lab now. All this work is from previous stuff because I've only been a professor for less than a year, but I hope to have some more of those things to show you folks next time around. So thank you very much for your attention, and I'm happy to take any final questions.
Have you tried running the disentanglement strategy on just like, let's say, stairs? So
yeah,
this automated type step.
Good question. Can we use the automated can we do automatic stair climbing sort of emergently by using that reaction strategy? I think the answer would be yes if we made a general locomotion controller that was more accommodating of varying height in the terrain. Right now, the controller we've got here would not behave very well if it ran into that large slope. But I think in theory, that should be extendable to that. And that was actually one of the tasks that I simulated. I simulated having sort of stairs or hurdles that were very rigid that the robot could slide its limbs over. And it worked pretty well in those cases. Yeah, good question.
On the previous slide, I saw an attachment on Salto's foot. It was like a claw almost.
Yes.
Do you have any other attachments similar to that, or is that enough, like the only other alternative?
Yeah, okay. So the original foot design is just a point foot, but we did do some other work that's still ongoing, not published yet, on getting the robot to jump between branches, and that involved adding that claw. Hopefully we'll have that out soon. We also, for the balancing control stuff in this one, added a little T-bar across the foot because we said we're just interested in the planar motion for right now. The propellers are not sized for this task very efficiently, and so we use that T-bar so the robot could tilt forwards and backwards, but not as much left and right. Sort of like training wheels. So that was another kind of foot design that we used. Yeah, in the back.
Another Salto question. So, like, you showed the video of it jumping against the wall and doing that. But like in the video, it showed that there was pretty good friction against the wall for it to go like this is the ball socket joint.
Yeah.
If it were to slip, I know you said you got rid of the self-counter kind of idea for the vectoring of like error. Is it kind of SOL, or can it
So the robot's foot does slip just a little bit when first hitting the ground and leaving the ground. And you can think about that as the spring in the leg goes to zero length, goes to rest length, the force along the leg goes to zero, but I could still use my reaction wheel to apply lateral forces. So the foot will probably slide a little bit during the stroke, during the jump. But if the foot really starts slipping a lot and the angle of the leg exits the friction cone, to use your words, yeah, you're probably SOL. Yeah, Shane, go ahead.
For the disentanglement work, is the retraction motion pre-programmed, or is that proportional to like the force or something?
The reaction strategy we use for disentanglement is monitoring the momentum-based observer force estimate. So it will continue pulling the leg until the force is detected to be low. At that point, then it can go back to its previous strategy. So it's not exactly pre-programmed in that it is reactive to when the force is removed. But the main initial motion is very similar each time.
I'm curious about the design decision to use the propellers
Yes.
in one axis and the reaction wheel in another. I understand you've got to run in one direction, but was there more to it than that?
The main reason for the propellers and not like more reaction wheels was a packaging issue. If you want to have an effective reaction wheel, it needs to have a large diameter. But the bigger the diameter, the harder it is to pack a bunch of these at different angles. So we figured the propellers were an easier method for that. Though I am now interested in looking at multi-reaction wheel solutions for that same problem.